Okay. Building cost of a heap. All right, so from last part, we estimate the upper bound of the total cost to do the max heapify for a given level, any given level, level H. So let's continue from there. We want to combine the cost of all heights. Yeah, because when you build a complete heap, you need to look at nodes from all heights. Okay, yeah. First, let's bring that previous formula here. Start from there. Cost of max heapify for all nodes of height H. That's what we get from part B.1. Yeah. Now, we apply this formula for different H. What are those H numbers we want to apply this formula? We want to look at that first. The heights we want to apply this formula. From 1 to floor function of log of n, log base 2. So we know this LG is log base 2. Okay, log base 2. Yeah. All right, log base 2. Okay. Why this number? Right? Why this number? The height. Okay? Yeah. Because here I want to give you a little more detail. All right. So given a heap, all right, yeah. All right. Right. All right. Because the reason we use this high number, we do not include those leaves. Yeah. Because those leaves, they correspond to height 0. And at all the leaves, we do not do max heapify, right? You do not need to do max heapify at the leaves. So that's why we do not include leaves. Okay. All right, so the height of these numbers, they do not correspond to leaves. Okay, yeah. All right. Now the total cost, like this. Okay, yeah. The upper bound, this upper bound, but we accumulate for all levels except leaf. Because for leaf, the max heapify cost 0. So even you include it, no contribution, 0. Okay, yeah. All right, so now let's estimate this summation. Yeah. First, we remove the ceiling function. When you remove, we use a larger expression, +1. So that will be greater than that ceiling function. Okay. All right. Then, because you have this +1, we separate two parts. Okay. The first term and the second term. Yeah. But the second term easier to calculate than the first term. So we work on the second term first. Okay. Like this. All right. This one, the second term, yeah, because it is the summation h from 1 plus 2 plus 3, all the way to the last integer, that is the floor function of log of n. Okay? That's like this. Okay? Thus we can apply the formula, well-known formula, but yeah, actually, you know, you can use less than or equal to, right? Yeah, yeah, because this big O, so we know that big O is not that precise. Okay, this big O notation we just put there for convenience, right? Yeah, put there for convenience. And here the big O calculation not very rigorous. The big O calculation, remember? So every time when we do big O related asymptotic notations calculation, not very rigorous. Yeah, just a simple way to represent our idea. All right. So that's why. So here we can use a larger number than the floor function. Use log of n. Okay. Then approximately log of n squared. Yeah, because the plus 1 can be omitted. Okay. Yeah. So we get this asymptotic class. Okay. All right. Next, we need to estimate the first part. Yeah. For the first part, yeah, h is a variable. H changes from 1 through that number, but the n we treat as constant. N does not change in this evaluation. No change. So for that reason, we can move n out of the summation. And also, we do not need to consider the big O. So let's just calculate the part. At the end, we add the big O back. Okay? Yeah. When we do the calculation, we do not need to include big O. Okay? So now let's estimate this expression. Okay. All right. To estimate this summation, we enlarge it a little bit. So we allow the number of terms go to infinity. So then we use more terms. So we get a larger number here. But this, even the larger number, it is still can be controlled by some expression of h. Yeah. So let's do the calculation here. Yeah. All right. Here we use a special technique. Yeah. How to do it? The trick. Very nice trick. Okay. With double S. When we double S, we change the denominator. 2 squared change to 2. 2 cubed change to 2 squared, and so on. Right? Yeah. So you can see, and basically we are doing term shift. Okay? Term shift. Yeah. Shift one term to the left. Okay? 2 cubed shift to 2 squared term. Okay? Term shift like that. Okay? Yeah. All right. Then you can see if we want to do some operation between these two formulas, these are the like terms because they both have the same denominator. The like terms. Okay? So we combine these like terms. So we do subtraction. Okay? So S equals, yeah, because the difference, the numerator of the difference, all 1. Okay? So the very nice structure. Okay? So we can find this geometric series. So this is a geometric series. So I hope you know the formula. Okay? Geometric series. Okay? Yeah. I hope you know the formula. Okay? Yeah. So this formula, if I really write it out, what's that? Y is 1. Yeah. So 1/2 times 1 over 1 minus 1/2. Okay, yeah. Or if I write a plus ar plus ar squared plus, infinite many terms, but the r must be less than 1. Then it is convergent. If r greater or equal to 1, it is divergent. So less than 1. So here I equals 1/2. So the geometric series convergent. Then the formula equals a times 1 over 1 minus r. Okay? So that's this, equals 1. Okay? All right, so we find it, 1. Okay? So then we get, so we put that big O back, put that n back. Okay? Yeah. So this whole thing 1 times n, right? So you have n there. So 1 times n, then we put the big O back. So we get big O of n. Okay? Yeah. So that is this estimate. Okay? Remember, when we build a heap, we also need to pay another term, the cost of another term. But this one is dominant. Okay? This n, dominant log n squared, dominant that growth function. So we drop it. So we do not need to consider it. We just use the dominant term here. So that is the building cost of a heap, big O of n. Okay? Yeah. All right. Example of summations. Yeah, in the previous slide, we did a summation, so using a special technique called term shifting technique. So here I want to give you 2 more examples, give you just a little more experience related to that term shifting technique. All right. Look at this example. So I changed the denominator from power of 2 to power of 3. The idea is exactly the same. Okay. So let's do the transformation. Yeah. All right. Here, when we do transformation, we want to take advantage of the structure. Here, the structure we have here. Okay. Yeah. Term by term, right? Term by term, the structure. All right. How to understand the general term? Yeah. In our analysis, we want to look at the general term, n over 3 to the nth power. That's the general term. In this general term, there are 2 parts. First, the coefficient part. The second, I tried to find a name for it, but I searched the web. I couldn't find an appropriate name for this part. So here, let me temporarily call it unipart. Because the whole thing we call a term, so here, let me call this temporarily unipart. So I hope later I can find an appropriate name for it. Yeah. So our plan, we change the unipart without altering the coefficient by that term shifting technique. Okay, yeah. All right. So we multiply that base number 3. Yeah, here the base number is 3. We multiply that. So we shift term. Okay, so we get this new representation. Next, we use the difference method. We take the difference of 2 series, okay, yeah, and combine like terms. Okay, yeah. So we get 2s left-hand side equals, so 1, then the second term, this one together, right? So 1 over, then next, like this, okay, yeah. Then, this is a geometric series, so we apply the formula, yeah, I gave you in the previous slide. We get this number and simplified 3 over 2. But that's 2s. We want to find a 1s. Okay, so the 1s divided by 2, so 3 over 4. That's the answer for the first example. The second example, I want to change the structure a little bit. So not a denominator, so this time it's a multiplication, not division. Not infinite series, finite series. Because in this case, infinite series will not be convergent. So we cannot consider the infinite series. It must be a finite series. All right. Transformation, the same technique. We multiply 3 both sides. Still, so doing the term shift. The base number 3. Then we do subtraction. 3s minus s. So we get 2s left hand side. So the right hand side, 3s, this last term, we put here. Then you minus 1, so you put a minus parenthesis here. Then this 1 times 3 minus 2 times 3, so that is a negative 1 times 3. 2 times 3 square minus 3 times 2 square, that is the minus 1 times 3 square, and so on. All right. So then the summation formula, so I hope you still remember this summation formula. So we need to use it. Here, that formula, if you do not remember it clearly, so let me write A plus AR plus AR squared plus A times R to the negative minus 1. Okay. If you see this summation, you can take A out. Then Rn minus 1 over R minus 1. So here, what do we use here? Okay, Then let's simplify it. We get this expression. Divided by 2 both sides, so we get this final expression. Okay, all right, Hope for the math calculation like this, so you can handle. So you need to understand and practice. We will have some questions like the examples we have here in your homework, assignment, and tests. All right, so we complete part 2. B.2.